20C. Question 1. One public opinion poll uses a simple random sample of 1,500 drawn from a town with a population of 25,000. Another poll uses a simple random sample of say 1,500 from a town with a population of 250,000. The polls are trying to estimate the percentage of voters who favor single-payer health insurance. All things being equal, 1, the first poll is likely to be quite a bit more accurate than the second. The second poll is likely to be quite a bit more accurate than the first. There is not likely to be much difference in accuracy between the two polls. Why 3? It's the sample size that matters, not the population size, unless what? Unless the population is very small. So if your sample size, right, if your sample size and your population are about the same, or are close in size, then you run into problems by putting people back in. Yeah. But if you never put anybody back in, then you don't have to worry, right? Because as long as nobody shows up twice, it's really not going to matter. Okay, 2. You have hired a polling organization to take a simple random sample from a box of 100,000 tickets and estimate the percentages of ones in the box. Unknown to them, the box contains 50% zeros and 50% ones. How far off should you expect to be if you draw 2,500 tickets? All we need to calculate here would be, we need the SE of the percentage. Do I care what the expected value is? No, because it's 50%. Right? Uh-oh, Tom's here. So in the box, we have 0.5 zeros and 0.5 ones. Do we care how many tickets are in the box? No, doesn't matter. Okay, so the SD is simply 1 minus 0 times the square root of 0.5 times 0.5, which is 1 times the square root of 0.5 squared, which is just 0.5. Okay. Now, I need to multiply that by the square root of, so 0.5 times the square root of 2,500. Oops. What does that tell me? So I'm expected to be off plus or minus 25, what are we drawing? I don't even remember. Ones. Okay, but instead of looking at 25, we want to compare that as a percentage. So I'm going to divide that by 2,500. Oops. I'm 1 0 off. It should be 1%. I got happy fingers. So 1%. For the next one, 0.5 times the square root of 25,000, and then I'm going to divide that by 25,000, and I get 1/3%. Right? Okay, and then 0.5 times the square root of 100,000, and then, oh, I'm missing that, divided by so that's 0.1%, 0.1%. Okay. You're going to find out later that actually 100,000 draws is a really bad idea, because we're going to start, so eventually we're going to quit looking at the box and just look at the sample. Okay, and then use the sample to guess what's in the box. And then we're going to start saying things like, I think there are more than 50% or less than 50% or equal to 50% ones in the box. And it turns out when you start making those statements, if you do too many draws, you might actually be more accurate than you're interested in being. So 100,000 draws is not really a good idea. Well, you'll see, because it comes down to something like this. So if I said, I believe the box has more than 50% ones, and I do 100,000 draws, okay, and I find out that it's 50.000001, then I would say, yes, there are more than 50% ones in the box. But 50.00001 is really just 50. Does that make sense? So you might be saying the box is greater than 50%. And if you only do 1,500 draws and you say yes, that would mean 51 or 53 or 55, something like that. But if you do 100,000 draws, you might find out that you get 50.000000001. And you say, yes, I'm 99% sure that the box contains more than 50% ones. But really, it contains 50% ones, right? So sometimes it's bad to do it. In this case, it wouldn't really matter. Okay. 3. Survey organization wants to take a simple random sample in order to estimate the percentage of people who have seen a certain television program. To keep the cost down, they want to take as small a sample as possible, but their client will only tolerate chance errors of 1%, 1 percentage point or so in the estimate. Should they use a sample size 100, 2,500, or 10,000, you may assume the population to be very large. Past experience suggests the population percentage will be in the range of 20% to 40%. Ooh. So what do we need to do here? Let's build a box. What would we expect to be in the box? How many people are expected to have watched the television show? Somewhere between 20 and 40. So let's call it 30. So what's in the box? 0.3 ones and 0.7 zeros. So the SD is going to be the square root of 0.3 times the square root of times 0.7. So the square root of 0.3, 0.3 times 0.7. So my SD is 458. Okay. Now, we could, you guys know how to, so you would times by the square root of 100 and divide by 100, right? Times by the square root of 2,500 divided by 2,500. Multiply by the square root of 10,000 divided by 10,000. Let's look at this in a different way. If I want a 0.01 error, how many draws do I need to make? So 0.01 is equal to, what's the formula for the standard error percentage? So it would be the SE number divided by draws. Right, well, we don't need to multiply by 100 because So the SE of the number is just the SD of the box. Well, because I put it in decimal form. Right. So the SD of the box times the square root of the draws divided by the number of draws. What's the SD of the box? 0.458. So let's just work this backwards. 0.01 is equal to 0.4583 times the square root of D divided by D. What is the square root of D divided by D? No. Square root, yeah, square root of D divided by D. It would be D to the 1/2. So, square root of D over D. What is the square root of D really? D to the 1/2. Right? So what's D to the 1/2 divided by D? Okay, this was supposed to be the easy part. Watch this. Right? Alexis? Isn't that true? So this is just the square root of D times the square root of D. So those cancel. So this is really just 0.4583 over the square root of D equals 0.01. Because that's how we learned it. Well, I mean, that's the simplified version, but that doesn't make sense in your head. Like, you would have to memorize a formula as opposed to understanding a process. So it just makes more sense to teach it that way, because SD over the square root of D doesn't mean anything. Right? It doesn't logically make sense. So what do I do here? Times by the square root of D. Now what? Divide by 0.01. So divide by 0.01, and I get 45.8 equals the square root of D. How do I solve for D? Square it. And I get 2100. What does that mean? If you make 2100 draws, assuming that 30% is correct, you will get a standard error percentage of 1%. Okay? Now, apparently, we don't want to ever do that by how difficult that was. So, just type in 100, type in 2500, and type in the higher one. Now, when you do 100,000, you get an error that's less than 1. So why don't you want to do 100,000? Nope. Right, it costs too much. The problem said you need to be as accurate as possible while maintaining a low cost. So if 2,500 works, if that's good enough, don't do 10,000. 10,000 will be more accurate, but it'll cost more. Okay? All right. 4. 100 draws are made at random with replacement from each of the following boxes. The SE for the percentage of 1 among the draws is smallest for box SE percentage. They're all the same. Okay? Is the SE for numbers going to be any different? No. Nope. Yep, the size of the box does not matter, as long as the number of draws is small compared to the number of items in the box. Okay? All right, 5. A box contains 2 red marbles and 8 blue. 4 marbles are drawn at random. Find the SE for the percentage of red marbles drawn when the draws are made with replacement and without replacement. Okay. So let's do with, because that's easier. With replacement means you put the marbles back in. So in my box, I have 2 1, or wait, we're doing reds, right? 2 1s and 8 zeros. I don't like that box. What's a better box? 1 1 and 4 zeros. Now I can do that because I'm putting them back in, right? If you don't put them back in, you have to use the original box. Okay? So the average of the box is going to be 1 divided by 5 is 0.2. Right? We could even change this box to be 0.2 ones and 0.8 zeros. Right? Oh, actually, let's do that. That's actually easier, right? Because it asks me for the SEP, which means I don't need this. Okay? So the square root of 0.2 times 0.8. So I get the SD is 0.4. And I'm going to multiply that by the square root of, how many draws are we making? 4. Okay, so that's the SE number equals 0.8. Now what? So the SE of the percentage is 0.8 divided by 4 is 0.2, which is 20%. Okay, so we will expect. It just converts it from decimal to percentage. Yeah. I always didn't like when they put the 100 in the formula. Well, so 0.8 divided by 4 equals 0.2, but this is the SE of the percentage. So it's give or take 20%. Well, this answer is a percentage. None of the other answers were percentages. Right? This calculation, none of the other calculations up there are percentages. They're all just numbers. But this one is a percentage, so we have to convert from decimal to percentage. Okay, so 20%. So we would take the expected value, give or take 20%, and the expected value is actually 20%. So what's the chance of getting 4 marbles? 20%, give or take 20%. Okay. Now we do the same thing without replacement. Well, it's kind of complicated, but we do have to use this first box. And now we're not going to put the marbles back in, which makes it a lot harder to calculate. Okay, so go to page 368, and there's the formula. So the SE without is equal to the correction factor times the SE with. So the CF times the SE with. So the correction factor is right there. So the correction factor is, so the square root of the number of tickets Okay, so the formula is at the bottom of 368. We take the square root of the number of tickets minus the number of draws divided by the number of tickets minus 1. This formula is, it's kind of like a standard deviation formula, but it's not going to go into how it found this and why you do the subtract 1. So if you look at it, it's basically the leftover tickets divided by the tickets minus 1, right? So if I take the total number of tickets and I subtract the number of tickets I took out, what am I going to get? The leftover tickets. So basically the CF is the square root of the leftover divided by the number minus 1. The number in the box minus 1. So if I take 4 tickets out of the box, how many are left? 6. There are 10 in the box. So I take out 4, and I'm left with 6 over 9. So the square root of 6/9, and I'm going to multiply that by do you guys see that? We take the CF and we multiply it by the SE percentage. So, and here, Jayla, do I put 0.2 or do I put 20%? It doesn't matter, as long as you understand the difference between the two. So if I multiply this by 0.2, now I have to change it to 16%. Okay? So what does that tell me? What does 16% tell me? So we would expect 20%, give or take 16%. Okay, why is this more likely? Yeah. So we would expect 20%. Right. Well, and it makes sense, right? We would expect to pull out 2 marbles, right? Well, if we are drawing without replacement, what's the chance of getting 2 marbles? Pretty high. There are only 2 in there. Can we get 3 red marbles? No. So if I drew 10 times, what's the chance of getting 2 red marbles? 100%, because I pulled them all out. So if I drew 9 marbles, what's the chance of getting 2 reds? Pretty high, right?
Yeah, because you pull all of them out but one.
You pull all of them out but one. So that the more draws I make, the smaller that SE becomes. No.
Because there's 2 red
If so, oh, I see what you're saying. If we cut the population in half, it would be close to the same, but you would miss those half steps. But yeah, the even numbers would be the same, but the odd numbers wouldn't exist. But in the end, you would make 5 draws and 20% would be red. So yeah, that's a good point. Okay.